Hi, my name is Ashlee Byron. I'm going to show you a couple of the more difficult parts that I modeled for this Model 20 Briggs & Stratton engine that actually is from the Lady Eagles Baja car on campus. So we split the main engine block up into 3 different parts. This was my part of it. This was basically these holes are all for mounting. One cool thing about this part was I learned how to use the user-defined pattern by making these outer holes here. These holes mount this part onto the main block, which all the internals are included in. One thing about this part kind of intimidated me at first because of the odd shape it was. Kind of took me a while to figure out the best way to measure everything and make sure it fit onto the rest of the block, but I ended up doing a pretty good job on it, in my opinion. It actually ended up fitting, so that was pretty good. For the drawing of that part, I decided not to dimension it just because it would be an eyesore ultimately. I did a couple different section views and a front view, labeling the hidden lines in the background, which the part was shelled in the back, so that's what it was showing on that drawing, and the center lines of the holes and the center line of the part as well. I'm going to talk about the big gear assembly. This is one of the 4 gears that I ended up modeling. This is an assembly of it. It went below the conrod and the piston. And how to make all these teeth here, I figured out the best way to do it was to make one of the teeth and did a complete crown circular pattern around this profile here. And then, like I said, I added in the lobes and the shafts, and this was one of the sub-assemblies I was responsible for. Next sub-assembly was the carburetor assembly. I started with the housing here and added on the pins, this switch here, which actually moves. I was trying to get a simulation down on it, but right now kinematics are not working out ultimately, but I'm still going to try to get that done by the due date. And same thing with this handle as well. I'm going to try to get that working. Now under here, this is a plastic float. It basically prevents the carburetor from being flooded with gasoline, and all the gasoline fits in this cup down here. And once the cup fills up too much, the float actually closes the inflow to the cup. So that's pretty neat. I actually learned about that a couple days ago. Then just a little overview of the internals of the engine. These are some of the gears. This is a shaft that attaches to the cam lobes, and those in turn attach to this conrod right here that we modeled in class for our pistons. And this is the piston here that attaches to that conrod and the shaft. Once this turns, this piston goes up and down in this terminal here, and that's a little bit about how the engine works. It's a little more complicated than that though.
My name is Andrew Shaffer. My major component was the engine block, to which all other components were fixed. The first thing I learned was using GSD in a reasonable and easy to understand manner. Initially, I'd thought that you needed 3 unique parts which could then be assembled into one final part. First of all, the lines and planes, then the surfaces, and then finally the solid body itself. Not only was this an extremely confusing way to make the part for me, it was clunky and was simply a difficult way of working and was not flexible in the least. Now, I was unaware, starting out with this project, of the ability to have multiple part bodies in a single part. Ergo, my thinking that we had to make those 3 different parts. Though I did ultimately end up modeling 3 other parts in this same way, I was able to go back and fix those. I did discover an extremely unique and helpful way of removing surfaces that are overlapping with the extract feature. The extract tool allowed me to extract a profile of lines around the section that I wished to cut. In this case, the interior surface of the engine block, which didn't trim it the way I'd hoped to. However, doing this gave me the perfect cutting surface in the trim command. The final lesson I learned was the use of the stiffener tool. The stiffener tool allows for the easy and flexible creation of fins, such as these. The stiffener tool simply uses an open profile, of which I have 2 shown here for this heatsink, and here for all of these rear heat sinks. This tool is unique, as the profiles used do not have to be closed and can be created without any complex geometry from the part itself. For example, the actual combustion chamber here. Finally, this tool is unique because it allows these complex features to be created with less sketches than a rib and are more flexible than a normal pad. The next part I worked on, the muffler, was the first one that I feel used proper and flexible part creation with multiple part bodies in a single part. These multiple part bodies include the surfacing for both the heat shield in the back and this small bracket on the side. Thus, all of the surfacing and solids are included in a single flexible part. The final issue I came across was in assembling the springs on the throttle assembly. Their hooks lacked any appropriate axis, surface, or lines with which to coincidence them to their mounting holes. Thus, I decided to create coincidence sketches with points and lines in useful locations, with which to assemble from. For example, points to surfaces and lines to center lines. This method proved effective. The GSD Connect tool also proved useful in making complex geometries in 3D space with minimal time effort, such as these connecting segments on the spring, and in creating the flexible hosing which wound around the engine. The generation of these parts was simple, requiring only the 2 lines to be connected, 2 points on those lines, and a given tension which would increase or decrease the radius of curvature of the resulting connection.
Hi guys, Skylor Wieland here, and the first part we're going to be looking at today is this red fan cover here. As you can see, this part has a lot of curved surfaces, which would typically make it difficult to model in the part design workbench. That's why for my work approach, I chose the wireframe and surface design workbench in order to make this part. So for my workflow, I usually start by creating an extruded surface, as seen here, and then simply create other intersecting extruded surfaces, such as the following one here, in order to create sections which I can then use the snipping tool to cut in order to give the profile that shape wanted for the part. Also with this part, you'll notice the circular pattern of holes on the top. That was done using a pocket command followed by a circular pattern in order to give it that fan ventilation shape on the top. The next part I'm going to talk about is the heat shield seen here. This was also created using the wireframe and surface design workbench. However, this part followed a different workflow. This time, I started by creating guide curve sketches, such as the one seen here. I then swept profiles along that, such as the one seen here, in order to give it that curved shape. So in the final, you'll see this creates a part like this. This process was then repeated for the various curved surfaces, such as the one seen here, in order to give the part its shape. Now, something interesting that was learned in the creation of this part was how when you have try to close a surface, sometimes you'll get 2 surfaces overlapping, which will cause CATIA not to close the surface. Now, what you can do if this happens is you can go over here to what is typically the boundary icon and simply select the extract tool, and then by clicking on a surface, it will extract that surface and you'll be able to delete the one specific one that's overlapping without destroying the rest of your part and allowing you to close it. The next part we're going to be looking at today is the rocker arm as seen here. Now this part attaches to the main block of the engine in order to house multiple of the components on one side of it. As you'll notice, there are a lot of parts to this design, however each one on its own is not very complex, as can be seen in the tree over here. Just a lot of pads, fillets, and mirror commands in order to make sure things are symmetrical. You will however notice a bunch of holes on the bottom and a bunch of oddly shaped ones also. This was important to be able to line these up with the holes on the main block of the engine, and so in order to do that and make sure they lined up correctly, we developed a technique which involved one of us creating the part and then taking the sketch of the hole positioning from that and copying it onto this part and then proceeding to place holes based off of that. So it gave us kind of a tracing for where the holes would go when you designed your part. The next part seen here is the exhaust cage. Note that this has a bunch of metallic bars placed in very specific patterns. In order to create these bars, I started off by creating profile sketches as seen here. I then swept a circle along those profile sketches in order to give the bars their rod shapes. Now, in order to apply these and create the cage form, a rectangular pattern was used as seen here in order to give them their patterns along each of the XY, YZ, and ZX axis. The process was then repeated in each plane in order to give all of the bars their shape and pattern as seen here.